Hello students. Let us start. So in the last class we have derived actually all the transverse components. So let us recall all those components because we are going today to learn about the TEM mode, TM mode and TE mode separately. So let us start with the TEM mode. Okay, so in the last class we have seen there are the transverse components. Okay, so this is EY component, this is EY component J divided by KC square minus beta dou of EZ dou Y plus omega mu dou of SC over dou X, and other two magnetic components are Hx is equal to J by KC square omega epsilon dou of EZ over dou Y minus beta dou of SC over dou X. The last component was, if you can recall it, this is J by KC square omega epsilon dou EZ over dou X plus beta HC over dou Y. Fine. So this was the transverse field equations what we saw in the last time. Now let us try to have the ideas about the TEM mode. So basically it is defined here that EZ and HZ supposed to be 0. Okay. So TEM mode is defined as by putting here the EZ component and magnetic field of Z component should be 0. Now the thing is like if you see this two components are 0, so you will find that EZ and we have written all this EX, EY, HX and HY, all the transverse component in terms of only the EZ and SZ component. So the moment if you are putting all these components, the values of EZ and SZ, you will find that everything will be 0. Fine. So like this is not acceptable, I would say here. Okay, so like the thing is, what should we do so that the wave should propagate, okay, along the Z direction, having the idea here the EZ and SZ is equal to 0. So basically the condition we can find here, these transverse component EX, EY, SZ and HY will be non-zero only when Kc is equal to 0. Okay, so the moment actually the Kc is equal to 0 or the cutoff wave number is 0, then it is, you will see here that it is forming a form of 0 by 0. Okay, what is that? This is indeterminate form, and this results actually the transverse field component. Fine. So this is one basis actually by which one can get these transverse field component. Fine. So now let us see this zeroed valued cutoff wave number, what this yields to us. Fine. So because we just saw that considering Kc is equal to 0 will make them alive actually, this all the transverse component. Okay, so if we have this 0 actually, so we may recall this relation from the last class, k square beta square, this is 0. So this will definitely will give you beta is equal k is equal to omega under root mu epsilon. Fine. So this is one thing. Okay. Another is that, okay, the Kc is equal here at the cutoff, so we can write omega c. Okay, the cutoff, c stand for the cutoff, under root mu epsilon. Okay, and we may also write down these things 2 pi fc. Okay, in terms of the frequency, mu epsilon is equal to 0. Okay, and this will lead to fc is equal 0. Okay, so here if you see, this is, let's say, equation number 2. So this is the first equation. It shows that the phase constant beta, okay, of the TEM mode on the guided structure is equivalent to the phase constant of a plane wave propagating in a region characterized with the same media, okay, between the two conductors of the guiding structures. Whereas the second equation, if you see, it shows actually the cutoff frequency of the TEM mode is actually 0 hertz. Okay, it's 0 means DC actually, and this means that the TEM mode can be propagated at any non-zero frequency, assuming the guiding structure can support a TEM mode. Okay, fine. So if the TEM mode supported by some guiding structure, yes, okay, this frequency is possible to propagate. Fine. So this is one thing actually. Now let us try to find it out. Another very important component, okay, which is we call as a wave impedance. Okay, so it is really very important when this TEM wave is propagating, we should know that the wave impedance. Fine. So now let us recall once again from the equation what we studied actually in the last class. Okay, so I can take a new page here once again. So yes, we can recall some of the equations what we wrote in a previous class. So it was J omega epsilon Ex is equal dou Hc over dou y plus J beta Hy. Remember these things? Okay. Another equation was, if you can recall actually, this was J omega epsilon Ey is equal minus J beta Hx minus dou Hz over dou x. And the third equation is J omega epsilon Ez is equal to dou Hy over dou x minus dou Hx over dou y. Okay, in a similar way, like other equations could be also formed for Hx, Hy and Hz. Now the thing is, because here we are defining the TEM mode, okay, so definitely we should recall the properties of the TEM mode, and we aware these things that it should be Ez and Hz component should be 0. Okay, so you can identify those components here, okay, Hz and all these things. Fine. So you can find some equations here, and you can definitely write these things. Like from these equations you may write Ex is equal k times of omega epsilon Hy. Fine. Similarly, from this equation you may write Ey is equal minus k divided by omega epsilon Hx, and of course the last one, it will offer you a very unique thing, which is dou Hy over dou x is equal to dou Hx over dou y. Okay, so here you can find actually a very important relations between the two field components of Ex and Hy, okay, and Ey and this is Hx. Fine. And of course we have a third relation, which is again a very important, that the variation, okay, of the hy component with respect to x and the variation of hx component with respect to y is same. Fine. So this is one conclusion from this equation. The same set of the equation could be found if you can recall actually the component hx, hy and hz. Okay, so I'm directly writing here the outcomes, okay, and then we'll summarize. Fine. So if you write for the magnetic field these things, so this will be hx minus k divided by omega mu, ey hy is equal k by omega mu ex, and of course again here ey over dou ey over dou x is equal to ex over dou y. Fine. Fine. So we have a 6 set of the equations here. Okay. Now here we are going to define a very important property, as I already mentioned, which is a wave impedance. Fine. So simply, like if you see this 6 equations considering the TEM mode only, okay, so you may conclude like this. If you take the ratio, you will find that ex over hy, fine, is equal to k over omega epsilon, fine. And from here actually, if you see these things, another relation could be obtained, in terms of omega, okay, which is omega and mu. So this could be written as omega mu over k. Fine. You check this equations actually, this equation. So if you take the ratio ex and this hy, okay, so you can write omega mu over k, and from the previous equation you will find that hy and ex, you will find that k by omega epsilon. Fine. So this leads actually under root mu by epsilon, or you can say this is eta, and which is equal to wave impedance TEM mode. Fine. So this is one thing. Now another set of equation we can also recall to write here, like minus ey over hx is equal to k over omega epsilon, and of course omega mu by k in a similar sense. So this will be also give you the same result, mu by epsilon is equal to eta, and of course this is z TEM. Fine. So now we define the wave impedance actually in terms of the material properties and by taking the ratios of these field components. Okay. Now let us more generalize these things so that this could be used in a further analysis too. Fine. So basically, if you see in journal, we may write these things like ex is equal to z TEM hy. This was one equation. Another was that ey is equal minus z TEM hx. Fine. So this is the wave impedance, okay, we written here. Now from this result, I was talking about the generalized equations actually. So these equations actually, okay, we may write like this: h x comma y is equal to 1 over z TEM az cap, okay, curl of E of x comma y. Fine. So hopefully you remember these parts actually, H and E. Fine. And what is that actually? These are the longitudinal component we defined actually at very start. These things I can recall once again. So it was like that E, okay, vector E is a function of x, y, z. So we may write these things. Vector E is a function of x, y, okay. This is a longitudinal transverse components. Sorry, this is a transverse component plus, just a minute, plus what is that? That EZ component, the longitudinal component, okay, which is again a function of x, y, and of course this is AZ cap and e to the power minus j beta z. In a similar sense, like we can write for the magnetic field as well, okay, longitudinal and the transverse components. Fine. So basically if you see here, you will find that we written actually these things in terms of the transverse component, because you see that we have all the results here, correct? You find this thing, Ex, Hy, Ey and Hx all are the transverse component. Fine. So basically if you see this equation, you will find that we have wrote this equation in terms of the again the transverse component in a generalized way. Right. So basically we may remember this equation, okay, to relate our the wave impedance to the transverse component. Fine. Hopefully this is clear to all. Now because like we are talking about the TEM mode, okay, and hopefully you know that this should satisfy the respective the wave equations, okay. The TEM mode, what I'm saying, the TEM mode, okay, must satisfy the wave equations. Why? Because we are talking about this traveling wave and all those things, correct? So it is quite obvious. So can we recall these wave equations? Yes. Yeah, we know these things. This is del square E plus k square E is equal 0, and the same is true for the magnetic field as well. Now what we want to do actually, because this is fine, like we want to solve these equations so that we can get these longitudinal components. So once you are getting these one component, you can define the transverse component as well, okay. So we can do a little exercise here defining these field component once again. So now just a minute. So we can write E, the function of x, y, z is equal to E, the function of x, y, e to the power minus j beta z. Fine. And what else? The h could be written x, y, z is equal to h, okay. This is a vector, okay, x, y, e to the power minus j beta z, okay. So recall that previous equation, okay, that z component will be vanish, okay, because this longitudinal component for the TEM wave are 0. Fine. So yes, of course we can write these two equations. Fine. Now these equations must satisfy, okay, the wave equations. Fine. Okay. So you supposed to replace, okay, those E and H in a wave equation, and you can solve, okay. So like let us try to find it out a generalized way to solve these things, because we have to solve the two separate equations. One is del square E plus k square E is equal 0. Another is del square h plus k square h is equal 0. Fine. So we have these two wave equation, and yes, of course, we need to satisfy these things. Fine. So let us try to do all those things in a rectangular coordinates. Okay. And here you can see actually these things, del square e or del square h. There is mathematically these two forms are same actually. So let us write down a generalized way, okay, so that we can talk about solution for these two equations. Fine. So what I am going to do here, okay, so in rectangular coordinate system, okay, let us write another variable, let's say f. Fine. Okay, instead of writing h and e again and again, let us make another this things vector here f actually, and we'll solve, and then after we'll replace f in place of h and e. Fine. So yes, so what we can write actually like this, del square fx ax cap plus del square fy ay plus del square fz az. Fine. Yes, we may also expand like this, dou square fx over dou x square plus, okay, because we are dealing with the del operator here. Yes, so yes, we can further expand these things like this, plus del square fx over del z square ax cap plus, okay, del square fy x square plus square fy over y square and of course ay cap, and then plus the last term would be dou square fz over dou x square plus dou square fz over dou y square and plus dou square fg over dou z square, and of course this is a z component. Fine. Fine. And what is f here is actually, so we can write f is actually is ex ey in journal actually, and hx and hy. Fine. Fine. So all the time we supposed to do the again and again this analysis, so better to let a third variable and solve it, and then we'll be replacing all the things. Fine. Okay. Now once again recalling these things, del square dou square f over dou x square plus dou square f over dou y square plus dou square f over dou z square plus k square f. Fine. Yes, we can write, because why? Because we started like that, del square e plus k square e is equal 0. Remember these things? Okay. So the del square e actually we have seen, okay, how we can expand these things, and this k square e is k square, and in place of e we put it f actually. Okay. The reason is quite clear actually, because we want to solve for both the wave equations. Okay, that is why. Okay, so now let us further solve it this thing. So dou square f over dou x square and dou square f over dou y square. Fine. Plus, okay, what about this term? What about this term? What we can write these things? Remember these things? So yes, so just a minute. Yes, so in place of this actually, okay, what we can do, minus beta square f, fine, plus k square f. Fine. These are all vector actually. Fine. Now this is 0. Fine. So this thing actually, if you common it out, this f actually, this is kc square. So now better to write dou square f over dou x square plus dou square f over dou y square plus kc square f. Fine. Now if you recall actually, for the TEM wave, okay, this is supposed to be 0. Fine. So we left with what is that, dou square f over dou x square plus dou square f over dou y square is equal to 0. Okay. Now we all aware about what is f actually. F basically ex, ey, hx and hy. Fine. So recalling these components, you may write different equation with the different field components. Fine. So let us write down these things. Just a minute. Okay. So what we can do actually here, yes, we can write, yeah, we just derive dou square f over dou x square plus dou square f over dou y square is equal to 0. Okay, this was the thing. Fine. Now I'm saying that because f we know, okay, f, what is f? F is actually ex, ey, hx and hy. Okay, so basically we can write here the 4 equations. Fine. So let us write down these 4 equations. These 4 possible equations will be dou of ex over dou x square plus dou square ex over dou y square is equal to 0. Okay. Another is that you can write dou square hx over dou x square plus dou square hx over dou y square is equal to 0. This is ex and hx component. Similarly, you can also write dou square ey over dou x square plus dou square ey over dou y square is equal to 0. And yes, the last equation will be, can you guess? This is hy in terms of hy. Okay, you can write plus dou square hy dou y square is equal to 0. Fine. Okay, so basically now we have this result actually for the TEM mode. Fine. Okay, so this results actually could be summarized in a compact way also. Fine. So how we can write a compact form considering all these things? Fine. So yes, we may write del t, okay, vector e x comma y is equal to 0, and of course dou, this is a square, t h x comma y is equal to 0. Okay, and what is this del t? Del t actually defines here the transverse Laplacian operator. Okay, fine. What is that? This is a transverse Laplacian operator. Fine. And here you can see these all are representing the transverse component, which is ex, ey, hx and hy. Fine. Okay. And like if you're working in a rectangular coordinate system or cylindrical coordinate system, accordingly like these Laplacian operator could be recalled or changed actually. Fine. So now we can summarize the TEM mode. So from these results actually, the transverse field of the TEM mode must satisfy the Laplace equation, and definitely with the boundary condition defined by the conductor geometry of the guiding structure, it is essential. Okay, so this is one thing. and the TEM transfers field vectors, which is that E and H, okay, are identical to the static fields actually for the transmission line. Okay, so this allows us to solve for the static fields of the given guiding structures geometry to determine the field of TEM mode. Fine. So yes, we can find finally the EX, HX, EY and HY. Fine. So this is all about the TEM mode. Fine. So yes, we can do actually, and basically if you can recall, this two conductor system and all, fine, supports the TEM mode. Okay, now so another is the T and TM mode. Fine, so let us quickly try to finish this part also. So yes, so let us talk about the TE mode. Fine. So if you talk about the TE mode, okay, so EZ will be 0. Fine. So similarly, like we have seen in a previous these things, okay, you supposed to recall that equations, generalized equation, and you supposed to replace Ez with the 0. Okay, so the moment you are making the Ez will be 0, so you can write all the transverse component like this: minus j omega mu over kc square dou hz over dou y. Okay, Ey is equal j omega mu kc square dou hz over dou x. And what are the two components? Hx is minus j beta over kc square dou hz over dou x, and the last one is hy is equal minus j beta over kc square dou h over dou y. So clearly you can see that all these transverse component, okay, defined in terms of the hz. Can you see these things? Where? Everywhere. Okay, it is defined with the hz here. Fine, because here the ez is equal to 0. So if you can fix hz, the problem is solved. Okay, now so another thing is that the cutoff wave number here, okay, we saw for the TM mode also. So here the cutoff wave number kc must be these things are non-zero. Correct, we'll see here. Okay, so now let us first try to find it out, the individual field components, the transverse component, by finding the hz component first. Okay, so hopefully you can getting some sense here that how we can find actually the hg in a similar way, like we supposed to once again recall the wave equation we have to satisfy, and yes, that will be a second order differential equation, and finally you can solve it. Okay, so let us recall. Okay, so we'll do the quickly here. So what we can do actually, yes, we can write down like dou square hz over dou x square dou square hz over dou y square, and of course dou square hz over dou z square plus what is that, k square hz is equal to 0. This is what? This is the wave equation. Fine. And we saw actually how we can write these things, and finally you can write this equation dou hz over dou x square plus dou square hz over dou y square plus kc square hz is equal to 0. Fine. So this is the final equation. Okay, this is the final equation. Fine. And what is hg here? What is hg here? Can you guess? Okay, yes. So here basically, if you can recall, okay, how we written this h is x, the function of x, y, z, and we have segregated like this: vector h, x, y, okay, transverse component plus longitudinal component. Remember these things? Yes, a z cap, and of course e to the power j beta z. Fine. So here simply we may get here hz component is a function of x, y, z as hz is a function of x, y e to the power j beta z. Fine. What you're supposed to do, you're supposed to put here. Okay, you're supposed to replace these things, and finally you can write actually a differential equation like this: dou square hz over dou x square plus dou square hz over dou y square plus kc square hz is equal to 0. That's all. So now this is the differential equation you supposed to solve actually to get this hz. So the once the hz is solved, okay, the problem is solved actually for the TE mode, because the moment you are putting the hz value, okay, in those equations, you can find all the transverse components. Okay, now another part is like the similar way what we did actually for the TE mode. We supposed to define here the wave impedance once again. Fine. So how we can define the wave impedance? This is ZTE. Okay, ZTE, and we saw these things: Ex over Hy also minus Ey over Hx is equal to omega mu over beta and k eta. You can also write this k eta upon beta. Fine. Now here you see a very important thing, that the wave impedance for the TE mode, okay, is a function of frequency. But if you can recall the TEM mode, you will find that that was not the function of this thing's frequency. Fine. In a similar way, like you can define the TM mode also. Fine. Like we define the TE mode, okay, by considering the hz is equal to 0. In a similar sense, actually defining the TM mode is quite similar, like hz is equal to 0. Now the moment you are defining hz, once again you supposed to write Ex, Ey, Hx and Hy in terms of Ez. Fine. And similarly you supposed to frame here the differential equations for in terms of Ez, and that differential equation will give you the solution, and that could be used to estimate the transverse component here: Ex, Ey, Hx and Hy. Fine. In a similar sense, actually you can define here the wave impedance for the TM mode, and it is actually, of course, we are defining like this. In a similar sense, Ex over Hy is equal minus Ey over Hx is equal to beta over omega epsilon and beta eta over k. Okay, so again here this is a function of frequency. Fine. So this is all about the TE, TM and TEM modes. Fine. So hopefully these things are clear to you. So what you can do actually, whatever we got these equations of Ex, Ey, Hs and Xy, okay, so that equation could be coded in MATLAB, and you can see actually, okay, how the things are varying actually, these things. Okay, So this is all about for the TE, TM and TEM mode, and next class we'll see the waveguide. But before the waveguide, we'll try to see the parallel plate system, and then we'll define the proper waveguide things. Okay, so okay, thank you. Yes.